Hello students, I hope all of you are doing well. So in this video we will be discussing gravitation chapter from JEE and NEET point of view. All these topics we will be covering one by one. Let us start. So the first topic that we will be discussing is law of gravitation. What does your law of gravitation says? Law of gravitation tells that let's say if two masses are there, m1 and m2, and they are separated by a distance of r. Then law of gravitation states that the force between them, the attractive gravitational force between them, is directly proportional to product of masses, and it is inversely proportional to square of separation between them. When both of these are considered, the relation is given as force is equals to G m1 m2 by r square. G m1 m2 by r square. Over here G is our universal gravitation constant and its value is 6.67 into 10 power minus 11. Unit for G is Newton meter square by kg square, right? Kg square. Now many students have difficulty in remembering this unit, so it is very easy to remember. If you notice, G can be written as what? F r square by m1 m2. G can be written as F r square by m1 m2. F is Newton, r square will be meter square, unit of r square meter square, m1 m2 will be kg into kg. So Newton meter square by kg square. This is our universal gravitation constant value, right? So the force, this is our relation that we should keep in mind, right? Now over here there are certain points that we should also consider while remembering this your law of gravitation. What are these points? First point is that it is attractive in nature. Gravitation force is always attractive in nature. Second point, it always acts along the line joining the two masses. Acts along the line joining two masses. So if I consider this one, it will be attractive and it will be along the line joining the two masses, right? Third point is it is applicable for point masses. It is valid for point masses, but it can be applied for large spherical bodies also. This third point that I am drawing over here is that for large spherical bodies also we can apply your law of gravitation. Over here the separation r will be considered from center to center, C1, C2. Let's say M1 and M2 large spherical bodies are there. So in this also we can apply G m1 m2 by r square for large bodies also, but for large spherical bodies the separation will be considered from center to center, right? So all this is about your law of gravitation. We can also write your gravitational law in terms of vector form. So how do we write in vector terms? Let us see. Okay, so I have considered a situation. How do we write down your law of gravitation in vector terms? In vector form. So let's consider a situation where two masses m1 and m2 are there and their position vector are r1 vector and r2 vector, right? So if we want to find out force on 2 due to 1, let's consider this is the separation between them. We are writing it as r. This is basically the position of 2. This is your r vector is the position of 2 with respect to 1. What can we write it? Over here if you see this triangle law, if we apply triangle law by our triangle law of vector addition, we can write down r vector will be r2 vector minus r1 vector, right? Now over here force for second will be acting in which direction? Force will be towards m1. This will be force on 2 due to 1. Force on 2 due to 1. Let us write down. So force on 2 due to 1 vectorially will be written as magnitude is G m1 m2 by r square, and it is opposite to this r vector. The direction is opposite to the r vector, so which I can write as minus r cap. That means r cap is the unit vector for your position of 2 with respect to 1. We know r vector is your what? R2 minus r1. So this one further I can write as f21 is equals to G m1 m2 by r cap can be written as r vector by r, which becomes ultimately your r vector by r cube, and this negative sign comes over here, right? So this is your law of gravitation in vector terms. Over here, r vector is basically r2 minus r1, right? Now, once we are done with this, we can also discuss something known as your superposition principle. We can also discuss something known as superposition principle. What is our superposition principle? Up till now, we have discussed that if two masses are there, the magnitude of force is g m1 m2 by r square. What if more than two masses are there? So let's consider a situation. Let's say that over here you have four masses m1, m2, m3 and m4. Now, or I'll take it another figure, 1 minute. Let's consider that a triangle is there, and at the vertices of triangle, three masses m1, m2, m3 are placed. m1, m2 and m3 are placed. Fine. Now, if we want to find out force on 3 due to net force on 3, that means over here total 3 masses are there, then in these cases we take help of superposition principle. Superposition principle is basically your vector addition. So force on 3 due to 1, where it will be towards 1, so we can write force on 3 due to 1, this will be the direction. Force on 3 due to 2, what it will be? Force on 3 due to 2, this will be the direction, right? Now, if we want to find out net force on 3, it will be basically the vector addition of individual forces, which I can write as F31 plus F32. So what is our superposition principle? Superposition principle is when more than two masses are involved. When more than two masses are involved and we want to find net force on any one of them, then first of all we find out force between two, that means between individual pair, between the pair of masses, and then find out the vector summation of individual forces. That will give us the net force on any mass, right? I hope this is clear. So this is all about your law of gravitation. Next, let us move to our gravitational field. So next we are looking at gravitational field. So first of all, field concept. What is field concept? Field concept is basically used to understand your non-contact forces. In this chapter, to understand gravitational force, we study gravitational field. In electrostats chapter, with electric forces, we study electric field. In magnetic effects of current, to study magnetic forces, we bring your magnetic field concept. So whenever non-contact forces is there, field concept is considered, or field concept is used. Now, coming back exactly to our gravitational field. Gravitational field. What is gravitational field? So theoretically, if we have to define gravitational field is, let's consider a mass m is there. Gravitational field due to mass m is defined as the influence of the mass in its surrounding, due to which other masses will experience a gravitational force. I'll again say it. Gravitational field due to a mass is the influence in its surrounding, due to which another mass will experience a force. What is the direction of gravitational field? Gravitational field is always towards the mass. Gravitational field is always towards the mass, right? Next, if we have to write mathematically, what is the relation given? So gravitational field G is given as force on a unit mass. Gravitational field, mathematically it is written as force on a unit mass. Due to this mass, it will be, let's consider this small mass m we are considering. So force on a unit mass, that is termed as your gravitational field at any point. So over here, let's consider this is m mass is present at a separation of r. Fine. It is a vector quantity. Obviously, the direction of gravitational field is towards the mass. So it's a vector quantity. What is the SI unit? SI unit, you can write down meter per second square. It is same as acceleration because force by mass. So unit is meter per second square, or basically your Newton per kg. Same, right? This is the SI unit. Next, let us discuss your gravitational field due to a point mass, that is G due to point mass. G due to point mass, if we have to write. Let's say that this mass capital M is there, and at a point P which is present at a separation of r, at a point P which is present at a separation of r. So what is the influence of this capital M mass at point P which is present at separation r? Mathematically it will be force by mass. So if we consider a small mass over here, so gravitational field will be force on that small mass m will be how much? G capital M small m by r square divided by force by m. So ultimately what are we getting? G is equals to gm by r square. This is your gravitational field due to point mass. This is your gravitational field due to point mass, right? Fine. Now next further we will be looking at gravitational field due to different bodies. For example, gravitational field due to a ring, gravitational field due to a line wire, gravitational field due to solid sphere, due to hollow sphere. One by one we will see all of them. Okay, so the first element that we are looking at is your gravitational field due to ring. In gravitational field due to ring, we will consider two specific points. First is at center and then at axial point. Let us first focus on at the center. So let's consider a ring of mass m and radius r is there, right? Over here the result is at the center point gravitational field is 0. Why it is 0? Why it is 0? So gravitational field at the center is 0. It is 0 because first of all gravitational field is a vector quantity. So if we consider, let's suppose you consider a small element over here of mass dm. At the opposite end of diameter there will be another small element of mass dm. Due to each one of them gravitational field will be towards the mass. So we can write dg and this is also dg. Like this, at for each element there is another element present at the opposite end of the diameter, and therefore the net gravitational field at the center will cancel out and it will become equals to 0. Okay, fine. Let's move ahead to our axial point. First of all, what is our axial point? The point over here, a point P which is present at a distance x on the axis of the ring, a ring of mass m and radius r. How do we find out gravitational field at axial point? So it's an integration. We are not going into the derivation of it. Just I will quickly summarize it for you people. So over here a small element is considered of length dl. Due to this small element gravitational field at point P, it will be, if I join this point P, this line over here, it will be towards the mass. It will be dg, right? It will be towards the mass, this small element of length dl. Now this dg will have two components. One component will be, this will be dg cos theta, and vertical component will be dg sin theta, right? What is our separation of this point P from this small element? Root over r square plus x square, root over r square plus x square. Now like we have considered this dl element, similarly all the elements, if you consider, the vertical component of gravitational field will cancel out. If you consider another element over here at the opposite end of diameter, the gravitational field, the vertical component will come out downward, dg sin theta, right? Similarly, due to each one of them, the vertical components will cancel out. So only a horizontal component, which is your dg cos theta, will be remaining. Now what is being done is, to find out your gravitational field, this dg cos theta is integrated for this whole ring, right? Now once we integrate this, finally the result that we get is g value comes out gmx. The result that we get is gmx by r square plus x square whole power 3 by 2. Gravitational field at axial point due to a ring is gmx by r square plus x square whole power 3 by 2. Result should be there in your mind, right? Now gravitational field, obviously it will be towards the center. That means if we consider for points which are towards right, field will be towards left. If we consider for points which are towards left, the field will be towards right. It will be towards the center because it's always towards the mass. The horizontal component will be all towards the center. Fine. Now if we draw a graph, between gravitational field and distance x, the graph will be coming something like this. This is the plot you will be getting, right? over here you will notice that at x equals to 0, gravitational field is 0. X equals to 0 is nothing but your center. So at x equals to 0, gravitational field is 0. At x equals to infinite, at far away distance also it is 0. It is maximum at point x equals to plus r by root 2 and x equals to minus r by root 2. This is a result that we must keep in mind, that G is maximum at x equals to plus minus r by root 2. G is maximum at x equals to plus minus r by root 2, and the maximum value, and how do we get this? Basically this result we differentiate it with respect to x and put it equals to 0, then this x value comes out to be r by root 2. So this result should be there in mind, that this distance is r by root 2, maximum is r by root 2. That means maximum gravitational field is at x equals to r by root 2. How much is the maximum gravitational field? So that result, when you substitute this r by root 2 over here, this G value, G max value will come out 2gm by 3 root 3 r square. This is the value of maximum gravitational field. This is the value of maximum gravitational field at the point r by root 2, minus r by root 2 plus r by root 2, magnitude wise it will come same only, right? I hope this is clear. So this result at axial point, this is the result. This is how we write down gravitational field at axial point. At x equals to plus minus r by root 2, we get maximum value, and the maximum value is 2gm by 3 root 3 r square, right? Next, let us look at other elements. So gravitational field due to long wire. Let's consider we have a wire whose mass density is lambda. Mass density lambda will be kg per meter, and they are asking us gravitational field at a distance r. So at a distance r, the gravitational field G is basically, G is given as 2g lambda by r, 2g lambda by r, right? Please keep this result in mind. Gravitational field due to a long wire at a distance r is 2g lambda by r. It will obviously towards the wire. So over here it will be towards the wire G. At this point it will be towards the wire G, right? Magnitude will be 2g lambda by r, and it will be towards the wire. Fine. Let's move ahead. Now we'll look at gravitational field due to hollow sphere and solid sphere, which are important. Okay. So next we are discussing gravitational field due to hollow sphere and solid sphere. First of all, hollow sphere. Let's consider a hollow sphere of mass m and radius r is there, right? Radius capital R is there. We'll consider 2 points. Point which is inside and points which are outside. Point which is inside and point which are outside. For inside points, what can we say? For inside points, small r is the separation of point from the center. So when small r will be less than capital R, that implies your inside point. For inside points, gravitational field is always 0, not just at the center. All points inside, everywhere inside, gravitational field due to a hollow sphere is 0. Next, if we talk about for outside points, for r greater than capital R, for outside points, please remember that spheres can be considered as point masses placed at the center. For outside points, spheres can be considered as point masses placed at the center. So what can we write it? For outside points, G will be Gm by small r square. Small r is the separation over here, right? Separation of point P from the center. This is for outside points, fine. This is for inside point. If we plot the graph, the graph will be coming something like this. G versus R, right? So the graph comes till radius, that means till surface, that is R is equals to capital R, your gravitational field is 0 only. It is 0 only. And for outside point, it varies. G is proportional to 1 by R square. For outside point, it is 1 by R square. So our plot will be coming something like this, right? This is the graph. Over here I have considered the magnitude. Acha, one thing I would like to clear, that let's suppose that in some cases if they consider direction also, and outward direction is considered as positive and radially inward direction is considered negative. So this graph will become below this. This graph will become below this. Over here this graph is for the magnitude. what I'm mentioning is, if let's suppose that radially inward direction, because gravitational field is always towards the mass, so it will be radially inward. If radially inward is considered negative direction, then this graph will be coming actually like this, in this below your r-axis, below x-axis, this plot will be coming. Fine. So this is your gravitational field due to hollow sphere. Now next is your gravitational field due to solid sphere. Important, we have to keep all the results in mind. Reason being that all the planets, Earth and the planets, that the cases that are considered, those are all are your solid sphere only. So let's say a solid sphere of mass m and radius capital R. Radius capital R. First of all, let's say for outside points. For outside points, I am considering, let's say, point P, which is present at a distance of R. Outside points means what? Small r distance will be greater than capital R. Small r distance will be greater than capital R. That means outside point. For outside points, whether it is hollow sphere or whether it is solid sphere, for outside points, you can consider sphere to be present at sphere can be replaced with a point mass placed at the center, right? For outside points, hollow sphere or solid sphere can be replaced as point mass placed at the center. So what will be a gravitational field for outside points? Gm by r square. This is for outside points. Fine. Next, for inside points, for r less than capital R, for inside points, G is given as Gm small r by r cube. Gm small r by r cube. This is your for inside point. This is for your inside point. For example, let's suppose this point is present at a separation of r and this point is inside. So for this point, your gravitational field is given as Gm small r is the separation, by capital R cube, capital R is the radius, right? This result, important result, keep this in mind. Now, if we plot the graph, the graph will be coming something like this. Magnitude graph, if we plot it, till r, it is varying linearly, and G is proportional to small r, G is proportional to distance, so it will vary linearly, and after that, there will be 1 by r square relation, 1 by r square relation. So this comes at your small r equals to capital R. Okay? At capital R, at surface, it will become Gm by capital R square. At surface, your gravitational field will become Gm by capital R square. So these are the results for your hollow sphere and for solid sphere. Now let us move ahead and look at acceleration due to gravity. Fine. Okay, next, acceleration due to gravity. So acceleration due to gravity is basically your gravitational field, what we discussed. What is a gravitational field? Force per unit mass, right? Force by mass we know is acceleration. So this is your G is acceleration due to gravity, force by mass. Now if we have to consider Earth, we will be discussing this acceleration due to gravity for Earth and for other planets. Now let's say that we have to consider, we have to write down G for Earth. So ME, mass of Earth, RE, radius of Earth. Now mass of Earth, ME is 6 into 10 power 24 kg, RE is 6400 kilometer. So if we have to write down this G value on the surface of Earth, it comes out to be Gme by Re square. Gme by Re square, acceleration due to gravity on the surface of Earth. And the value of this, when we substitute Me value 6 into 10 power 24 kg and Re value 6400 kilometer, change to meter, when we substitute, our G value comes out to be 9.81 meter per second square, something which we are very much familiar with, right? Now this is our acceleration due to gravity on the surface. This is on surface. Fine. Next, over here I would like to mention, please remember one thing also, from numerical point of view it is helpful. Gme, capital Gme can be written as your GRE square. Many a times in problem solving in last 3-4 steps of the calculation, this step is helpful to us, and so keep this result in mind. Okay, next, so this is your acceleration due to gravity on the surface of Earth. If we say acceleration due to gravity for any planet, if we have to write down, for a planet of mass mp and radius rp, what can we write it? On the surface of planet, for a planet on the surface of planet, gp can be written as acceleration due to gravity for planet P, it can be written as capital G mass of planet by radius of planet square, right? Next, also many a times this G is required in terms of density. Many a times it is required in terms of density. If let's suppose density of planet rho p is given, density of earth rho e is given. So in those cases, G in terms of density will be 4 by 3 pi capital G rho r. I am writing this general result that acceleration due to gravity in terms of density will be 4 by 3 pi capital G rho r. You can keep this in mind. Many a times questions are given to compare the acceleration due to gravity of earth and planet, or planet A and planet B in terms of density. So this result is helpful. Fine. Now we have seen that acceleration due to gravity, it depends on your separation, basically the distance from the center. This result we have written for the surface. On the surface of earth, GME by RE square. What if we are talking about away from the surface? What if we are talking about a point which is present at a height h from the surface of earth? What if we are talking about a point which is present at a depth d from the surface of earth? And as we know that G value, generally G value, what do we write it? For the solid sphere, it is given. For outside points, it is given as your Gm by r square. So as r value will change, your G value will also change, right? Gravitational field or acceleration due to gravity will also change. For the surface, it is this. But as your separation changes, as the particle or an object goes away, if we consider a point which is away from the surface or which is inside the surface, your G value will vary, and that is what we will be looking over here for your variation of G, right? So up till now we have discussed these topics. Now we are moving on to our variation of G with height, variation with depth, variation with shape, and variation with rotation of earth. Let us see. Yeah. So let us see variation of G. As we discussed that if we go above the surface of earth or below the surface of earth, your G value will vary. First we are looking at variation of G with height h. So what do we write down? General result if we have to see, so G will be GME by RE plus h whole square. Right, at a height h from the surface, your acceleration due to gravity will be GME by RE plus h whole square. Now mathematically, by solving it mathematically, we can get our result. The result that we get is G at height h. G at height h we get as G times RE by RE plus h whole square. Right, RE by RE plus h whole square. This is acceleration due to gravity at height h in terms of G at the surface, right? This is the result that we have to keep in mind. Now there are many confusions regarding your which result to use and what result to use. What I am talking is basically that there is one more result. What happens is, if let's suppose that this height, that is height of point from the surface, is less, radius of earth is your 6,400 kilometer. 6,400 kilometer, and if your h is very less than RE, that means we are talking about your less than 500 kilometer. For less than 500 kilometer, in this result only binomial approximation is used, and the result we get is G at height h is given as G times 1 minus 2h by RE, right? So two results we have got over here. First is this, second is this one. Yeah, sorry. So variation of G, so variation of G with height h, if now you have to check whether to use this relation or to use this relation. From the language of the question, it will be very much clear. If your h value is less than, or if we have to say this h value is less than 500 kilometer, in the question it will be very clearly mentioned that h is less than RE, or height is 20 kilometer, 30 kilometer, 60 kilometer, then we have to use this relation. G at height h will be G times 1 minus 2h by RE. If your height is comparable, for example half of the radius of earth, 3,200 kilometer, then we have to use this result. If it is 1/4 of the radius of earth, then we have to use this result. If it is 3 times the radius of earth, we have to use this result. Only for small distances, when h is less than RE, we have to use this result. To be specific, if h is less than 500 kilometer, in question it is 30, 40, 50, that is what is you will come across, right? Okay. Next, third we can say, so two results we got it over here. Next, this result is for H less than RE. Third is when we consider for 10 kilometer, that means H less than 10 kilometer. If we talk about G value is less than 10 kilometer, that means we are talking about very near to the surface. This is very near to the surface of Earth, and over here G value is considered constant, which is your 9.81 meter per second square. And therefore throughout our kinematics in motion under gravity, we considered G as constant and did all the question, because we were talking about motion very near to the surface of Earth. Now in this chapter we will be discussing when the particle is taken to larger heights, when it is taken to your 100 kilometer, 50 kilometer, or let's suppose 2 times radius of Earth, then variation of G is given by these two results, right? Okay, next let us look at your variation of G with depth. So next we have gravitational potential energy. Gravitational potential energy, how we define it? It is basically work done to make the system, to bring the configuration, to bring the system from infinite separation to that present configuration. What I mean is, let's consider a situation. Let's say we have two masses m1 and m2, and they are present at a separation of r. Then gravitational potential energy for this pair of masses will be work done to bring the system from infinite separation to this distance r. So U, gravitational potential energy, which is denoted, or U potential energy denoted by U, it will be work done, which will be integral of force into displacement. So G m1 m2 by r square into dr. It is brought from infinite separation to a point or at a distance r, right? When we integrated, the potential energy result we get is minus G m1 m2 by r. Now this is your gravitational potential energy for two masses which are separated by separation of, or which are separated by distance of r. Over here you will note that a negative sign has come. What is this negative sign indicating? Negative sign because gravitational force is attractive in nature. Because it is attractive in nature, work done against it will be your negative only, right? Therefore we get your gravitational potential energy is negative. This is for two masses. What if we have more than two masses, if we have multiple masses? So let's consider if we have multiple masses. I'll take a situation. For example, your three masses are given to you, m1, m2 and m3, separated by a distance of r12, r23 and r13. Then the gravitational potential energy of this system, which consists of three masses, will be given as, U of system will be given as summation of pair of the masses. That means summation of the gravitational potential energy of pair of masses. That means for potential energy of 1 and 2, for 2 and 3, and for 1 and 3. Because three masses are there, we'll have three pairs over here, which we can write as what? U12 plus U13 plus U23. Right? For individual pairs we can write, for example, in this case it will be, for 1, 2 it will be minus G m1 m2 by r12. For 1, 3 it will be minus G m1 m3 by r13. For U23 minus G m2 m3 by r23, right? So this will be your gravitational potential energy for the system. If we have four masses, let's consider another situation is given that at the vertices of a square four masses are placed. Then in that case your total 6 pairs will be forming. When we have four masses, total 6 pairs will be forming. So we will write down potential summation of potential energy of 6 pairs. That will give us the potential energy of the system, right? Next we can also write down your work done to change the configuration. Work done to change the configuration of the system. Work done, beta, if the configuration is changed slowly, that means without changing, slowly at constant velocity, then work done will be given as change in velocity. Work done will be given as change in velocity. This is work done by external force, which will be your, not velocity, I said velocity, sorry. So work done will be your change in gravitational potential energy. So whenever configuration is moved, it is changed slowly, then work done will be given as your change in gravitational potential energy, which is U final minus U initial. U final minus U initial. Fine. Let us move ahead and take a look at your gravitational potential. So gravitational potential, if we see gravitational potential, which is denoted by V, it is defined as gravitational potential energy of a unit mass in a gravitational field. How do we write it? It is given as V is equals to U by m naught, right? Potential is U by m naught, that is potential energy of a unit mass. The unit for this is basically joule per kg. Gravitational potential unit is joule per kg. Now as we know that, let's consider gravitational potential is a characteristic of point. What do I mean by that? Let's suppose that this mass m is there, and at point P, this mass will have some influence. That means it will have some influence. Due to this mass m, this point P will have some potential. Whatever is the potential energy of unit mass placed at this point, that is its potential. Now let's say that over here some mass m1 is brought, and the potential of this point is V. We are saying that potential of this point, that means due to this m mass, the potential of point is V. So if a mass m is brought over here, potential energy of mass m can be written as U will be mass into the potential, so m1 into V. If we know potential at a point, potential is a characteristic of point. Potential is a characteristic of point in a gravitational field region. So if we know potential of a point, if we multiply it with the mass, we will get potential energy of that mass, right? So this is it. Next we will be looking at some cases how to find out your gravitational potential due to your point mass, due to ring, and due to spheres. Let us see one by one. Okay, so first is potential due to point mass. What do we write it? So let's consider a mass m is there, and at a separation r, a point P is there. Then potential at point P due to this mass will be given as minus gm by r. It is given as minus gm by r. Potential due to a mass m at a distance r is given as minus gm by r. Potential energy, gravitational potential energy is negative. That's why we get potential also as negative only, because potential is potential energy of a unit mass. So minus gm by r. Fine. Next, if we see potential due to ring, what do we have? Let's consider two cases. First is, let's say that a ring of mass m and radius r is there at center point. At center point, gravitational potential will be, because potential is a scalar quantity. Potential comes from potential energy. Energy is scalar, potential is a scalar quantity. Therefore, due to all these elements over here, if we consider all the elements of the ring, due to all these elements, the potential will add up ultimately. It's a scalar quantity. So potential at center point comes out to be minus gm by capital R, right? I hope this point is clear. Next, if we take a look at axial point, if we have to consider, let's say a point P which is present at a distance of x on the axis, and this ring is having a radius of r and mass is m. What is the separation of point P from the elements of the ring? If you consider over here this distance is, this is r, this is x, so this distance is your root over r square plus x square. All the elements on the ring, all the points, if we break the ring into small elements, basically all the points on the ring are equidistant. That means it's kind of cone. If you will notice, it's nothing but a cone. If you will imagine over here, this is the tip of the cone. So all the points are from P point, it is at a separation of your root over r square plus x square. And as we know, potential is a scalar quantity. So due to all of them, the potential will add up, and your potential at point P, that is at axial point, it comes out to be minus gm by root over r square plus x square. Root r square plus x square is the separation. Root r square plus x square is the separation. Okay, so the results that we have got, this is due to your point mass minus gm by r, due to ring at the center point minus gm by capital R is the radius, and due to ring at the axial point, it is given as minus gm by root over r square plus x square. R is radius, x is the axial distance. Fine. Let us move ahead and take a look at your gravitational potential due to hollow sphere and solid sphere. Okay, let us see all the cases for your gravitational potential due to hollow sphere and solid sphere. First, let's take a look at your hollow sphere. So, let's consider a hollow sphere of mass m, radius is capital R. First of all, we are talking about a point P which is at outside point. For example, point P which is at a distance of r, small r, and this small r is greater than capital R. What do we mean by small r greater than capital R? This is your outside point. This is your outside point. Gravitational potential for outside point is given considering this hollow sphere, considering this shell as a point mass placed at the center, and therefore it will be given as minus gm by small r. Small r is the distance of point P from the center. Okay. For inside points, that is your r less than capital R, r less than or equals to also on surface and all the inside points, your gravitational potential is given as minus gm by capital R. It is constant throughout over here, because if you remember, gravitational field inside a hollow sphere is 0. Gravitational field inside a hollow sphere is 0, therefore there is no work done in moving it. So gravitational potential difference over here is 0, and that comes out to be, potential difference comes 0, but potential at the surface is minus gm by r, and throughout inside it is minus gm by r only. It's constant. So the two results that we have got is, for outside points minus gm by small r, for inside points minus gm by capital R, right? Let us draw the graph of V versus small r over here. So if I consider, let's suppose over here V is taken, and on the x-axis small r, that is your separation, is taken. For distance r equals to capital R, that means for all these are your small inside points. For inside points, how much it is? It is constant. This, it is constant, and its value is minus gm by r, minus gm by r. Fine. Next, if we consider, for outside point, V is inversely proportional to R, so our graph will be coming something like this. Okay, this is your graph for V versus R for hollow sphere. Okay, these are the results. Now moving on to our solid sphere. Solid sphere, let's consider solid sphere of mass m, radius capital R. First of all, let us talk about outside points. Outside points, that means your R will be greater than capital R. These are your outside points. For outside points, we can consider sphere to be a point mass placed at the center, and so it is something like this. Let's say that this point P is present at a distance of small r greater than capital R, that means outside point. For outside point, we can consider it as your point mass placed at the center, and therefore V will be minus gm by small r. Okay. For inside points, that is, for inside points r less than or equals to capital R, even on the surface also. So this is for inside points. V is given as minus gm by 2 r cube 3 r square minus small r square. Okay. This result is derived by the relation between your gravitational field and gravitational potential. So we can keep the result in mind. For us, it's a revision series, results are important. So for outside, and this is for inside points, right? For inside points, two results we can see, that is basically, 1 minute. First of all, let us draw the graph. During that only we'll discuss it. So if we draw the graph for it, if we draw the graph V versus R, if we draw it, beta, for outside points, it is similar relation is there. So this is your, let's say, small r equals to capital R. Over here, we'll draw it. This is what we are getting, right? At this point, this is the point at the surface point. This is your surface point. And at surface, how much it is coming? Surface means your small r will be equals to capital R. Over there, it will come out to be minus gm by capital R. This result is your minus gm by capital R. At center, this is your r equals to capital R. At center point, that means r is equals to 0. When you will substitute over here for inside points, that means at center, if we substitute r equals to 0, how much we will get it? R0, this r square by r cube. R square will cancel out. You will get it minus 3 by 2. I'll write over here minus 3 by 2 gm by r. And for inside points, it is coming a parabolic curve. It's a upward parabola because this is minus, minus will become plus. Your coefficient of r square is positive and it's a quadratic equation. So it will be a parabolic curve from this point. This is your 0 point to this point. This is the graph you will be getting like this. Okay? It's visible down. 1 minute. Now I think so it's okay. Please take a look at it. So all these results are there in front of you. These are for your hollow sphere. This is the graph of potential versus R for hollow sphere. This is for solid sphere, results for outside point, for inside point, and this is the graph of potential versus R for your solid sphere. See carefully over here. For solid sphere, for inside points, result is minus gm by 2r cube, 3r square minus small r square. At the surface it will be minus gm by r, whereas at the center it will be minus 3 by 2 gm by r. Graph will be coming. This will be the nature of graph, right? Okay, then let us move ahead. Okay, so now we are discussing escape velocity. What is our escape velocity? First of all, let's consider a situation. Let's say we have mass of earth. We are considering earth, saying me is mass of earth, re is radius of earth. A particle or a body of mass small m is there and it is being given some speed v. Obviously it will go away from the surface. So what is our escape velocity? Escape velocity is the minimum speed that should be given to a body on the surface such that it leaves the gravitational pull of the earth, How do we calculate it? For calculation, we use the concept that if it goes away from the surface, that means it goes away such that there is no gravitational pull acting on it. That implies there will be no interaction energy. Total energy of the particle with this should become 0. If total energy should become 0, what are the energies it is possessing initially? It is possessing kinetic energy and it is possessing the interaction energy, the gravitational potential energy. So we can apply over here mechanical energy conservation. What is our mechanical energy conservation? K initial plus U initial equals to K final plus U final. These are our initial energies. This is our total energy initially. Initial kinetic energy, if we write half mve square. Initial potential energy on the surface, we can write initial potential energy as minus g me mass of earth small m by re, right? Gravitational potential energy is minus g me m1 m2 by r. So over here it comes g me m by re. This is equals to, finally total energy must become equals to 0. When we simplify this, your escape velocity will come out root over 2 g me by re. Now we know that g me by re can be written as your, in terms of small g, root over 2 g re, right? But small g value on the surface, it is 9.81, re is 6400 km. When we substitute this value, escape velocity on the surface of earth comes out 11.2 km per second, right? So these are the results that we should keep in mind. This is our escape velocity result, root over 2 g me by re and root over 2 g r in terms of small g if you have to write, and its value is 11.2 km per second. Sorry. Now certain points that we can consider or we should remember regarding escape velocity is, escape velocity, if you notice, is dependent on mass of earth. That means depends on mass of planet. It is independent of mass of the object, mass of the body. So escape velocity ve independent of mass of body. First point. Second point, if speed, that means if speed is less than escape velocity, if a particle is thrown with a speed less than escape velocity, that implies it will not go away. That means it will not leave the gravitational pull. Either it will revolve around, start revolving around the earth's surface, around earth it will start revolving, or it will fall down on the earth. Then in this cases, you will come across, on the basis of this point, you will come across many questions. If a particle is thrown with a speed of half of the escape velocity, then find the maximum height reached by the particle, right? So you will come across these type of situation. When speed is less than escape velocity, how do we find out the maximum height? again we will be using our mechanical energy conservation. How? I'll show you. Initial kinetic energy, that will be your half mv square. Initial potential energy minus gmem by re, and final kinetic energy at the maximum height wherever it is reaching, it will be 0 plus potential energy. Because it is less than escape velocity, that means it is still having the interaction energy, which we will get it as minus gmem by, the separation is always taken from the center of the planet. Separation is always taken from the center of planet. So if this is re, this is h, so separation will be re plus h, right? This is a very common question. You will come across many questions where you will be requiring, if a body is projected with a speed less than escape velocity, 1 by 2, 1 by 3, 1 by 4, many times you will come across question, then we will be using mechanical energy conservation to find out the maximum height up to which the particle or body will reach. Okay, so we have discussed about escape velocity with respect to Earth, general relation and some points. Now some more things if we can write down. For a planet, if we have to write the result, basically this only same calculation will be done. Escape velocity for a planet can be written as root over 2g mass of planet by radius of planet, right? In terms of this also we can write down root over g of planet, radius of planet. Fine. Also you can remember escape velocity result in terms of density. In terms of density, what do I mean by this? So in terms of density, escape velocity is given as root over this g. We know earlier in the lecture we have discussed that this g in terms of density is your 4 by 3 pi capital G rho r, right? If you substitute over here, it will come out to be root over 8 by 3 pi G rho r square. That means your escape velocity in terms of density is proportional to your root over rho r square. That is density root over rho r square. This is our escape velocity in terms of density. Many times this is helpful. So if you keep in mind, it's well and good. Otherwise, during the calculation, you will have to derive it. Fine. So this is all about your escape velocity. Now moving on to our next part, which is your satellite motion. Fine. Okay. So next we are talking about our satellite motion. Satellite motion. So let's consider a planet of mass m is there and its radius is capital R, right? Radius is capital R. A satellite of mass small m is revolving around the planet. Satellite, let's say this satellite of small m is revolving around the planet at a altitude of h, then beta, what will be the radius of the orbit of the planet over here, which we write as your orbital radius, we call as orbital radius, and this small r will be capital R plus altitude h. Okay, now we have to find out certain parameters in your satellite motion. Your orbital speed, that means with what speed is the satellite moving, the time period of the satellite, and energy of the satellite. Let us see. First of all, to find out your orbital speed, what we will do is, which force is helping this satellite to move in circular path? Your gravitational force will be helping it. That means gravitational force will provide the necessary centripetal force. So what can we write? Force gravitation is equals to force centripetal. Force gravitation, how much it will be? G capital M small m by r square, orbital radius. Distance is always measured from the center of the planet or from the center of the solid sphere, which is planet. Fine. Gmm by r square. This is equals to centripetal force. How much we know it? M into v square by r. R cancel, m cancel. Your v square value comes out to be G capital M by r. That means VO, which is our orbital speed, is equals to root over Gm by r. Orbital speed is root over Gm by r. Fine. This is our one result. Second, we can find out our time period. If we see time period, this is our orbital speed. Next, if we have to calculate time period will be your 2 pi r by v. Just now we have calculated our orbital speed. When we substitute over here, our result comes out to be 2 pi by root gm r power 3 by 2. Okay, so the time period that we get is 2 pi root gm r power 3 by 2. So these are the two results that we should keep in mind. Orbital speed is root over gm by r and time period is 2 pi root gm r power 3 by 2. Certain points that we can observe from this is that orbital speed depends on mass of planet and orbital radius. It does not depend on mass of the satellite. It is independent of small m. It does not depend on mass of satellite. Similarly, time period. Time period also does not depend on mass of satellite. It depends on your this capital M, mass of the planet, and obviously orbital radius, right? Fine. Apart from this, we can look at energy of satellite. Energy of satellite. Okay. So what all energies it will be possessing? Because this satellite is moving with a speed, it is having motion, so it will possess kinetic energy. How much will be kinetic energy? Kinetic energy we know is half mv square. So half mv square, when you will substitute this orbital speed over here, your result will come g capital M small m by 2r. This is our kinetic energy. Next, is it visible down? 1 minute. Okay, next if we see potential energy of the gravitational potential energy, we know it is written as minus g capital M small m by r. R is the orbital radius. This is our potential energy. Next is if we find out total energy will be kinetic energy plus potential energy. If you add both of these, you will be getting minus capital G small capital M small m by 2r. So these are the results for kinetic energy, potential energy, and your total energy. Okay, from these results we can relate kinetic energy, potential energy and total energy as their magnitudes. That is, kinetic energy magnitude is equals to magnitude of total energy, which is half of the magnitude of potential energy. 1 by 2 times magnitude of potential energy, right? So these all are the basic quantities which we should remember regarding our satellite motion. I'll quickly summarize. Orbital speed root over gm by r. This m is mass of planet, not mass of the satellite. Root over gm by r. R is orbital radius, and orbital radius is given as radius of the planet plus altitude, height from the surface. Time period of satellite is 2 pi by root gm r power 3 by 2. Okay, energy of satellite, if we see, kinetic energy will be gmm by 2r, potential energy will be minus gmm by small r, and total energy will be minus gmm by 2r. So next, let us move to the next topic. Okay, so now we are discussing Kepler's law. Basically, Kepler's law, there are three Kepler's law which talks about the motion of planets about sun. So what we have is, first is law of orbits, second is law of areas, and third is law of periods. First, law of orbits. Law of orbits says that a planet will revolve around sun in an elliptical path, not in circular, in an elliptical path such that sun is present at one of the foci. Okay. Next, there are certain points regarding this elliptical path which we can keep in mind. First is, when planet is moving in an elliptical path, the speed of planet does not remain constant. Speed of planet do not remain constant. It is maximum at this point. This point, which is nearest to the sun, is termed as perigee. Over here, if I say Vp, is maximum at this point, and speed of the planet is least at the farthest point. This farthest point is termed as apogee. So Vp, speed at perigee, is maximum and V at apogee is minimum. Okay. Next, certain more points, let us discuss about it. One thing, if you notice over here, this gravitational force, when planet is moving in your elliptical path, gravitational force is helping the planet to move in the elliptical path. And as we can observe that gravitational force between sun and planet, this gravitational force on the planet will pass through the sun. If gravitational force will pass through the sun, that implies torque due to this gravitational force will be 0. If torque due to this gravitational force will be 0, that implies dl by dt is 0. dl by dt, that is rate of change of angular momentum, that is torque, will be 0. If that is 0, that implies your angular momentum will remain constant. So speed will change. When planet is moving in an elliptical path, speed changes, but what remains constant? Angular momentum remains constant. First. Second, Also, this is your only conservative gravitational force is acting. That implies energy will also remain constant. K initial plus U initial will be constant. Okay, fine. Let us move ahead. Next, we are talking about your law of areas. What does law of area says? Law of area says that the line joining, so we have sun, we have planet. This is the line joining the sun and the planet. And let's say that in time t1, this planet reaches from point A to point B. This planet reaches from point A to point B, and this line joining the planet and sun will sweep a area of A1. Okay. In time t2, the line joining sun and planet is sweeping an area of A2. That means planet moves from point P to point Q, and this line sweeps an area of A2 in time t2. Then second law, that is law of area, says that the line joining this will sweep equal area in equal interval of time, and from that what we get is that aerial velocity, that means dA by dt is constant. dA by dt is constant, and this dA by dt we get is equals to L by 2m. What is our L by 2m? L is basically angular momentum, m is the mass. Fine. Over here, from this we can also write down, as dA by dt is constant, if it is moving from A to B, the area swept is A1 and in time t1, from P to Q, area swept is A2 in time t2. From this result we can also write, as aerial velocity is constant, A1 by t1 is equals to A2 by t2. Right. So these are some of the result which we can keep in mind regarding our law of areas. Fine. Third, law of periods. It talk about your time period. What is the time period of the planet? How, on what factor it depends? So it says that square of the time period is directly proportional to A cube. What is A over here? A is our major axis. A is our major, or sorry, semi-major axis. As we know, this is our ellipse. In ellipse, this is 2a. So time period square is directly proportional to our cube of semi-major axis. Fine. Okay. Let's move ahead. Last we are discussing our double star system. So we have come to our last topic, that is our double star system. What we have is, I have drawn two figures, one by one, we'll take a look. Let's suppose two planets or two stars are there having masses m1 and m2. They are separated by a distance of r. We are saying that m1 is heavier as compared to m2. M1 is heavier, that implies the center of mass will be lying towards m1. Let's say that this distance is r1 and this distance is r2. Why we are talking about center of mass? Because when two masses are there, when they are free to rotate, why they'll rotate? They'll rotate due to the mutual gravitational force. They will rotate due to the mutual gravitational force, and when they are free, they'll be moving about their center of mass, right? If you notice carefully down, I have shown the figure. So this is the center of mass. About center of mass, m1 will be moving in a circle of radius r1 and m2 will be moving in a circle of radius r2. R2 is basically distance of m2 from center of mass. R1 is distance of m1 from center of mass. R1 and R2 we can calculate. We know from our center of mass relations, R1 can be written as opposite mass by total distance by total mass. Similarly, R2 can be written as opposite. For that it will be m1r by m1 plus m2. Okay. Now these two stars are moving due to the gravitational force. Gravitational force is actually providing the necessary centripetal force for their motion. We know that force gravitation between them will be how much? G m1 m2 by r square. And over here they will be moving with same angular speed. Their angular speed will be same. So this is with omega and this also moves with omega. They will be at opposite end of the diameters, always they will be. So for example, if it reaches over here, m1 reaches over here, m2 position will be over here. This will be m2, this will be m1. So they will always be at opposite end of the diameter and their angular speeds will be same. So what can we write? This is force gravitation for any one of them. For m1, if I write it, for m1, force gravitation is equals to force centripetal. Force gravitation G m1 m2 by r square is equals to m1 into acceleration centripetal, which we can write as r1 omega square, right? When we substitute this r1 value, we wrote it over here, m2r by m1 plus m2. So when we substitute over here, our omega value will come out root over g m1 plus m2 by r cube, right? Root over g m1 plus m2 by r cube. This is the angular velocity. This is the angular velocity of both the planets or both the stars, and they will be moving with same angular speed and same time period. Their angular velocity will be same, and their time period will also be same. Fine. And this will be the magnitude of your omega. I hope this is okay, right? So with this, we have completed our video, our discussion of all the topics. I hope you found the video helpful. Do consider to press the like button and subscribe to our channel. Thank you very much. Bye bye.